Okay, here we go. So the top one.
And the title is somewhere.
The top line.
Oh, the top line on geodesics and test black hole motion in Kerr. Or, okay, wrong title.
Yeah, thanks, Gabriele, and thanks to the organizers for the chance to speak. I wish I could be with you there in beautiful California, but this is good enough. So yes, I would like to talk about, I gave the title Geodesics, Test Black Hole Motion, and Kerr. Then I was thinking I wanted to talk about some new results on, just to read this, hidden constants for a quadrupolar test black hole in Kerr in the radial action for generic binary black hole scattering to g squared s to the fourth. Okay, we're probably not going to get to that, but I wanted to read that title. So let's, in fact, more talk about where are we, so the community, at with post-Newtonian, post-Minkowskian, spin. This talk is very much about spin. I would love also to talk about tides and absorption, but there's simply not time for that here. Of course, it's not unrelated, especially at the frontiers of these things. I'd also love to talk about neutron stars, but no time. So I'm going to very narrowly focus on black holes in binaries with aligned and generic precessing spins. I do want to talk about, not just aligned spins. Sorry. And self-force, if there's time. And all of these things are, of course, very much related. Here's some pictures of a binary. Say, actually, let me stick with red. And another fun thing, besides gravitational waves coming out of black hole binaries or scattering black holes, it's also fun to think about scattering gravitational waves off of a spinning black hole. And actually, I wish I also had time to talk about that, but also no time to talk about that very interesting thing. So before I move on to where are we at with spin in PN, PM. So we see here our binary, and I'm representing, so the spinning black hole has inside it a ring singularity of radius A. The spin is the mass times this ring radius. And of course, I'm using units where C equals 1, but not H bar nor G throughout the talk. And an interest, so also I want to focus a lot on, say, the test body or probe limit. But when you have spinning black holes, there's this funny, you could call it a spinning probe limit, where say one of the black holes, let's say that's our Kerr. Its ring singularity is hidden behind its horizon. That's our big M for Kerr and A for its ring radius. But then say I took the limit where, say I started maybe with another spinning black hole, but I took its mass to 0. I wanted to make it a test body or probe. Of course, if I do that at fixed ring radius, which for the little guy, I'm going to call that sigma. So that's the ring radius of this, if you will, test black hole. Of course, it's not really a black hole anymore. It's a naked ring singularity. If I took its mass to be, say, smaller than its ring radius. but that is a very interesting limit. That's another point I want to stress. Okay, then we move on to where are we at with PN, PM spin? So of course, there's a very long history, which I can't go into, of the post-Newtonian approximation, also post-Minkowskian approximation, applied to binary motion, also with spin. You know, I'll post, the slides will be posted. I don't have time to go through this at all, except just to circle some things like, you know, PN, EOB, self-force. And just in case someone here doesn't know what is self-force, here we wrote it up here. It's this kind of test body or probe limit, but perturbing away from that. So black hole perturbation theory, like in the limit where one guy is much smaller than the other, let's say it doesn't have spin. So it would follow geodesics in a black hole background, but then we consider the gravitational perturbations to that background caused by the little guy. And that's black hole perturbation theory or self-force. So there's a long classical history and some very interesting developments about connecting post-Newtonian and self-force, which again, I'm just gonna have to whiz through this. And you see in the last, so these are the first 4 digits of the archive numbers. In the last 10 years, there's been a tremendous amount of progress thanks to heroic efforts, especially besides this classical PN, in the effective field theory approach to post-Newtonian gravity or non-relativistic general relativity, pioneered by Goldberger and Rothstein, and many collaborators and others have picked this up. And again, if someone is upset about not being mentioned here, I apologize, and I'll be happy to add you if you let me know. But this tremendous effort, say, from the linear and spin or spin orbit interactions at the next and next 2 leading orders to the spin squared interactions, they were so hard, they often got split into these S1, S2, and S1 squared pieces onto next to leading order. And then let me start by highlighting one thing here, which is this, again, heroic effort by Michel Levy and Jan Steinhoff to do the next to leading order for PN, spin squared, completing the whole spin squared sector. This is one of these only results here that is yet unconfirmed by another group. And let me go locate that here. Where is that? Is this guy here. And also you notice if you wanted to do post-Minkowskian instead of post-Newtonian, you would have this guy complete with the G cubed S squared, which has not yet been done. Then let me next highlight this amazing work by the same 2 authors, where, and actually that was very much building on these leading order spin cubed and spin to the 4th effects here. Where, so Levy and Steinhoff wrote down a Lagrangian without yet, so there was still left the task of, say, integrating out the gravitational field in this PN EFT formalism, but they, in principle, wrote down a Lagrangian that should work to give the leading order post-Newtonian contributions to all orders in spin. That's what I mean by spin to the infinity. So let's locate, and then Jan and I, at first we were kind of just making a guess or extrapolating. Eventually we completely worked out integrating out the graviton from that Lagrangian. And so that's located here in this table. And let's see, eventually here, that was done for Post-Minkowskian, that same yellow thing. And many works since then have contributed to better understandings of that in different ways. And before I move on to amplitudes related things, I want to highlight a couple more things in this table. One of them being okay, so going into 19. Okay, let's look around here for a minute. And let's do this in green. Actually, okay, so I'm a bit disorganized here, but you can see it does have an order. This is chronological order at this point. And let me point to now. Yeah, this. So we heard a lot yesterday about Tutti Frutti. And that the birth of Tutti Frutti was in September 2019 when Bini Demore and Geralico showed us how to get most of 5PN from first order self-force. And that was crucially relying on this mass scaling argument that Thibault explained to us in December of 2019. Which, you know, now 2 years later, everyone takes it for granted that first and second post-Minkowskian orders include, of course, this includes the leading and next to leading post-Newtonian orders. These are, if you're clever, you can get those completely for arbitrary mass ratios from 0th order self-force, or really the test buddy limit. And you can get the third and fourth post-Minkowskian ones from first order self-force or linear in mass ratio black hole perturbation theory calculations. Okay, so that was the birth of Tutti Frutti, let's say, which has continued beautifully. That was used here, extended to spin, to predict for the first time the complete next to leading order 4.5PN spin orbit couplings. Coincidentally, the study of those in the PN EFT had already been initiated right there. I'm sorry, that's the wrong one. That one. And let's locate this on the table. That one is spin orbit 4.5PN here. Let me also circle this one in green, where the same authors here did not the full spin squared, just the spin 1, spin 2 part, and not for precessing spins, but only aligned at 5PN. And that's that second green thing I just circled on the table. And so again, this was using the so-called Tutti Frutti, if you will, or arguing for the polynomiality in the masses, as some people were calling it yesterday, or the mass scaling with aligned spin, using first order self-force black hole perturbation theory results to try to predict the results for arbitrary mass ratios, arbitrary masses. And so I have to admit, we weren't 100% sure that really was going to work out. I mean, we thought we could see that the mass scaling argument should hold, I even with spin, but we were ready for the possibility that it might not work out exactly like we expected with this Tutti Frutti thing. However, very nicely, just this month, more heroic efforts by an PNEFT from this time Kim, Levy, and Yin took the calculation all the way to a gauge invariant observable, the binding energy, which can be compared. And at least for this, let me, going way up here, where was that? Yeah, this guy was then at least partially confirmed by that result. And so that's really great. Very happy that we both got the same result for this piece of this thing, and that's really good news for both sides. And look forward to more fun stuff like that, made possible by, again, heroic efforts in the PNEFT. How am I doing on time, Gabriele?
You have still 15 minutes.
Including questions?
Yeah, unfortunately.
Okay, great. Okay, so let's go back and pick up the PM story, which for me at least started with, where are we? 2016. Yeah, this paper right here. And with spin, you know, it was really amazing to me. So I think many of you know with the post-Minkowskian approximation, of course, this was nothing new in 2016. There had been lots of work in the 70s, in the 80s, particularly. I think many of you are familiar with Westphal's 2 p.m. scattering angle. But yeah, I just really found it amazing that the first time anyone ever asked themselves, okay, what about post-Minkowskian with spin, was in September 2017 when Bini and Damore did that for the first time using this very nice spin holonomy trick, if you will, a very nice trick to get the first post-Minkowskian or G to the 1 result. Of course, that was continued here and in many other references. And just a small comment I want to make about, oh, the table's up here. Okay, so in terms of PM spin, so that was here with Bini Damore. And then I guess, okay, why not also circle this in blue? Starting with, for example, my paper, but also another very important paper, which I will get to in just a moment, which you see was coincidentally very close at the same time by Alfredo Guevara, where very impressively, he looked at amplitudes, let's say first at tree level. So there's this guy, basically one graviton exchange. That was built from these 3-point amplitudes, which even though the paper came out later, you know, Alfredo had a draft of the paper before it came out. They had given talks about it for months beforehand. In this very famous paper by Arkani, Hamed, Huang, and Huang, from now on AHHH, where they talked about, so scattering amplitudes for all masses and spins, including massive higher spin particles. And they argued that there was a definition of minimal coupling, which really was about having a uniquely well-defined high energy limit. which singled out some particular 3-point amplitudes, which Guevara put together in this one graviton exchange to get, like I'm saying here, the tree level, all orders in spin, amplitude, at least. And it was eventually made clear that that amplitude corresponded exactly to these classical results that started here, let's say. Also at 1 p.m., I should change that, 1 p.m. or all orders in G, all orders in spin at linear order in G. In that same paper by AHHH, they talked about the Compton amplitude. Sorry, so these should be amplitudes, not vertices. Really, these are cuts. They talked about this so-called Compton amplitude with 2 massive spinning guys and 2 gravitons. Of course, both of these papers also talked about photons instead of gravitons. But only up to spin 2, not for arbitrary spin. And so Alfredo in the same paper, again, put that together into this one loop process, where really the only important part is this triangle cut. And its mirror image. And that's what I wrote here. Oh dear. G squared, one loop, up to S to the 4th. Why S to the 4th? Well, that has to do with having these guys only up to spin 2. And I really should have mentioned an important, very important observation in this paper by Vaidia, working in PN at the leading orders, but that if you take a scalar and somehow take its classical limit, of course, you're getting a monopole. If you take a Dirac massive spin half field, you can get the dipole or the spin effect. If you take spin 1, you can get the quadrupole, a spin squared quadrupole. Sorry. Where was I? Quadrupole. Sorry. Quadrupole proportional to spin squared. Specifically, if you have minimal coupling, you get the spin squared quadrupole for a black hole. That was noted by Weige, and that was picked up by Guevara in this paper, arguing or conjecturing that these amplitudes from AHHH going up there should give me black hole scattering at these levels. So that is still a conjecture, I would say. And okay, so continuing that story, for example, there was this paper. So let me actually switch to purple now. Purple, there was this paper, which very much just took Alfredo's amplitude. So Alfredo had the amplitudes. There was an issue of interpretation maybe, or how to get to observables. But this paper went to the aligned spin scattering angles. Through those same levels, again, conjecture, let's say. And it took 3 years, but eventually Where are we? Here. Purple. This essentially the same GOV thing. Now, GOV, sorry, is Guevara, Ochirov, and me. That was aligned. And now this very nice work from 3 weeks ago or something like that. Yeah, November of this year. Did it for generic. Let's see, again, to this G squared S to the 4th level. And so you're not going to find this formula for, let me say this is the iconal in their paper, but this is like the GOV formula, kind of, or the GOV2 formula, but picking up some extra pieces that we missed, let's say, to get it correct for generic spins. I know
5
this
minutes.
is 5 minutes, including questions. Okay.
Yeah. Unfortunately, yeah.
Yeah. So, then in that case, that's a good stopping point. And I think many people are also aware of, the problem. So the boundary between spin 2 and spin 5 halves, or the boundary between 4th order and 5th order in spin, is a very interesting one for many reasons. And there was this very interesting work in August of this year, which addressed that to in a very interesting way. And I'm looking forward to see how that continues. And yeah, let me just leave it there and leave at least some time for questions.
That's good. Thank you very much, Justin.
Yeah. Mm-hmm.
Let's see if there are questions from the audience. Or if not, on Zoom.
I have a question.
Yeah, please go ahead.
Yeah, so what's the way forward for going higher spins above spin?
Right. Okay, so one possible answer is, let me uncross it out. Delete and this, delete. Okay, so one possible answer is what I was saying. So this, right, so it's an issue of this Compton amplitude, let's say, or, and in the unitarity approach, you get the one loop process from the Compton. The Compton has problems at spin to the 5th or spin 5 halves. How can we, even though it doesn't have problems at spin cubed and spin to the 4th, is it actually describing a black hole? How do you really know? Right? It is a beautiful amplitude with many nice properties. This AHHH spin 2, massive spin 2 meeting graviton's amplitude, but how do you know it's really describing a black hole? So you need to compare to something that has to do with a black hole. And if you look at also this Compton amplitude, it's like gravitational wave comes in, meets black hole, gravitational wave goes out. So it's like classical scattering gravitational waves off a spinning black hole, which is a problem that you can solve classically. So it is this black hole perturbation theory, not exactly in the self-force guys, but these self-force people are experts in, solving for perturbation, linear perturbations of black hole spacetimes. So we want to try to make this link between scattering gravitational waves off black holes classically and this Compton amplitude in the classical limit. And so solving the Tucholsky equation, that's just the name of the separated partial differential equation describing the gravitational perturbations or curvature perturbations of a Kerr background. So one possible way forward, I think, is making this link right here. There's a lot of other interesting things that I didn't even talk about, like, you know, so there are these bootstrapped amplitudes from AHHH, but there's important work which we're about to hear about from Andres. So it's okay that I didn't talk about it so much. Let me locate it here. Oh, that was already 2020 sometime. Here, where, you know, in addition to doing this EFT mashing and going to these levels, the point is they start from a QFT Lagrangian for a massive spin S coupled to gravitons. And that's another very important short link to make. Instead of just starting with these bootstrapped amplitudes, how are they related to QFT Lagrangians? Also possibly with nice properties. For that matter, how are both of those things related to world line actions, like of this very important paper here, which this Levi-Steinhoff Lagrangian, which, for example, if you will, roughly speaking, it's like kinetic terms plus spin squared times Riemann plus spin cubed times spin cubed, come on. Sorry. Spin cubed times grad Riemann plus spin to the fourth times grad squared Riemann, etc. Right, so that kind of world line action, how does that relate to these field theory Lagrangians a couple years later? How does that relate to these bootstrapped amplitudes? Those are also very interesting questions, which I think will help figuring out this link, because this link is rather non-trivial.
Other questions?
So maybe I can ask just
Sure. Who
this
is
question,
speaking?
Julio.
Oh, Julio, yes.
So about this question of whether the particles really describe black holes,
Yeah.
Would you ask the same question on the word line? And if
Absolutely, absolutely, yes. And so in the world line action, there are going to be Wilson coefficients, which of all kinds, and yeah, some of them. So there's this certain series that appears in this set of operators, which is linear in the curvature. Those are pretty much fixed if you want it to be a black hole. But then there becomes the issue of like Riemann squared terms, which really become most directly relevant, at least to the story that I was trying to tell, at spin to the fourth order.
those have to be computed using linear response, like the usual way of computing love numbers that people have used in the past.
So
Not dynamically, but
there is certainly a lot of work on, okay, yeah, so love numbers. So Wilson coefficients of Riemann squared terms could be called love numbers or related to tidal effects. So they're like an induced response, if you will. Love tides, that's like Riemann squared no spin. You could also have spin squared Riemann squared before you get to this spin to the fourth Riemann squared, and other things as well with derivatives and odd numbers of spin. But so yeah, there is a lot of work trying to figure out the coefficients here, which are these love numbers. And for black holes, there has never been a work yet that has said in 4 dimensions that these things should not be 0 for a black hole. Modulo, okay, things to do with absorption. maybe. However, it's still unclear in many of those works exactly how are these love numbers defined in that context. It's not clear how they should be related to these Wilson coefficients and these actions over here. So yeah, there is a lot of interesting, and I should take that back. In fact, there is work along those lines, I believe, quite recently, or at least in the last year or so. But yeah, a very interesting question. And of course, yes, there are all kinds of possible couplings, and we need to somehow try to constrain their coefficients.
Okay, well, I think we have to move on, but let's thank Justin for this very broad review of the situation. Thank you.